department, working on observations and instrumentation for the cosmic microwave background, as well as the evolution of the universe. Very big topics. He is actively involved in a number of observations, as well as he uses facilities like the Hubble telescope, as well as the James Webb Space Telescope. He is also the director of astronomy at the National Center for Supercomputing Applications, just next door, as well as the founding director of the Center for Astrophysical Surveys. So today we are welcoming Mr. Vieira to discuss telescopes, past and future.
Okay, thank you. So I did it's kind of easy to give a talk, especially when you have a limited time. The hard part's often like making it concise. So I have 160 slides, so I failed already. But I'm just going to skip over whatever, depending on what questions we have and what interaction we have. So feel free to interrupt, ask questions. I think this should have been 2 talks, past and then future, but we'll squeeze it in. We'll try to get to the stuff at the end. So what, just thinking about this in the big picture, why do we need telescopes? So the point of the telescope is to collect more light than we can collect with our eye, right? Which is about a centimeter aperture, 2 of them. But you can tell, we can make telescopes that are 10 meters diameter or even larger. Okay, so we can collect a lot more light than we can with our eye. So that allows us to observe fainter objects that we can see with our eye. And typically, more distant objects are fainter. So this allows us to see more distant objects. One other kind of crucial thing to keep in mind always when I talk about astronomy is that light travels at a finite speed. So the more distant object, we're not seeing it as it is, we're seeing it as it was. So naturally, a telescope is a time machine. An actual, honest to God, time machine where we're looking back in time across the universe. And we can look all the way back to the very beginning with telescopes. Okay, and I'll show you some of those. So that's just kind of where I'm coming from on this, is that I use these to study how the universe evolved over time. Okay. So a few kind of key parameters for telescopes. One is the aperture. If I say an acronym or a term that is not familiar, just stop me and we'll define it, okay? But I'm going to use these a lot. So aperture is the collecting area of the telescope, right? Resolution is spatial resolution is how fine a detail it can see. And typically, you design your optics to be diffraction limited so that your resolution will always go as the wavelength divided by the diameter. And you can scale that. You can just scale. So if you have a certain resolution, you double the aperture, you've doubled your spatial resolution. Caveat is that for a lot of stuff that we do on the ground, we're limited by the seeing in the atmosphere. So fluctuations in the atmosphere, but limit the seeing to about 1 arcsecond from the ground in the optical regime. It does not apply in the radio regime, and it doesn't apply when you get above the atmosphere. And then just to give you a sense of scale for these things, the moon and the sun in the sky are 30 arc minutes, half a degree. Human resolution is 1 arc minute. And 1 arc second, so 1/60th of that, is a good resolution from the ground. And 0.1 arc second is usually good from space. So just to give you a scale for these things. And then the third term, just remember exposure, which is how long you stare with the camera, okay? So how long you sit there and collect photons. And that's a powerful thing of once we developed photographic plates and kind of ways of digitizing, like converting photons into electrons and then digitizing that, is that you can get a lot of sensitivity by exposing them, right, by staring. Okay, so the invention of the telescope kind of corresponded with the end of the Renaissance and the scientific revolution, where a lot of people were starting to understand how the universe worked. There were technology developments that were happening. One of these was just the blowing of glass and the ability to make mass-produce glass that was really clear. And this brings us to Galileo, who's commonly referred to as the inventor of the telescope, but that you can debate that. People had like spy glasses, which you invert the image, but it was a military secret, basically, because you could spot a ship on the horizon sooner. So people knew about these things. They knew about simple optics. Like the Greeks and Egyptians even knew about you could take spherical pieces of glass and use it to magnify them, and use it for reading small print and stuff. So the idea has been kicked around. Galileo, for sure, is the first one to realize that we could use this to uncover kind of the nature of the cosmos by looking at it. So that unequivocally, like he wasn't the one that figured out how to make these. He figured out to point it out. And so he's the father of modern physics. He was a professor of mathematics at the University of Pisa. Physics really wasn't like a field. He studied motions, mechanics, materials. He was the first person to realize the importance of the telescope. He provided proof that the Earth is not the center of the universe and that the Earth orbits around the sun. He also studied astrology. He rejected elliptical orbits because he considered the circle perfect. And he had this totally bullshit theory of tides. So, you know, genius on one hand, like kind of kook on another, right? It's kind of interesting. So in 1609, with this telescope, which is there, and this was about the size of a baseball bat, had a 1-inch diameter of glass that he hand ground in like a tube. So he built this by hand. But with this 1-inch diameter telescope, he discovered the moons around Jupiter. So that immediately told you that the Earth is not the center of the universe, because he could see with his eyes moons going, things going around another celestial object. Okay? Boom. One observation proves the Earth is not the center. Then he saw phases of Venus, which immediately showed you that Venus is actually going around the sun. Okay? And then he saw craters on the moon, which showed that the universe was not perfect. Before that, like there was just an edict that said, you know, the celestial objects are perfect spheres. That's how it is. So this was really truly a revolution. He was politically savvy too. You know, he like gave one of these telescopes to who he wanted to be his future benefactor. Right? He would do things like this. This is an image taken from just a simple. Actually, I forget if I should have put a credit on this. I forget if I took this or my colleague took this. But this is basically what you can do with an amateur telescope from the ground. Just the camera taking a picture. Has anybody seen the moons of Jupiter? Really? Oh my God. So we have a National Historic Landmark on campus. The observatory, right off the quad. Open house every first Friday. Just go and with your naked eye, I'm sorry, not your naked eye. With that telescope, you can see these moons of Jupiter. If you take binoculars, like all you need, remember he had a janky handmade 1-inch diameter telescope. If you have a nice pair of binoculars, you can see this. It's trivial. If you have a spotting scope, the key is just putting it on a tripod will help a lot. The other nice thing is that these are so bright, you can spot the planets like by eye, and you know, half the time. So this is, you know, if you look with your naked eye, you see these in the show this. Export. I didn't touch it. Well, while we're trying to figure out the projector, all of those things that he discovered got him in trouble with the church. And he was called to stand trial in the Inquisition. And you know, on one hand, he had kind of political benefactors that were trying to protect him. On the other hand, you had kind of like religious workshops that were like literally trying to burn him. And he had people that he made enemies, and people were just kind of out to get him as well. But he navigated this fairly well, given his temperament. I mean, seems like a pretty cranky dude. At the trial, the popular legend, so he goes through this trial for blasphemy. He's doing all these things that are against, you know, what the teachings of the church. and he was found vehemently suspected heresy, which, you know, most people, that means you get burned. But they allowed him to go basically under house arrest on the condition that he didn't talk about this anymore. And he agreed. And the legend is he walks outside you know, the Vatican and stomps his feet and says, you know, and yet his text concerning two world systems was added to like the church banned list, and it was on that list of banned books until like 1835. But then in 1992, he was finally forgiven by the church for his studies. Okay, so next top on our tour is Newton. So Newton, you know, considered one of the greatest physicists of all time, invented calculus, described the way objects move, you know, all of classical mechanics, basically everything up until Einstein was Newtonian. Formulated mathematical description of gravity, etc., okay? He also worked in optics, dabbled in metallurgy, which at the time was basically witchcraft. But to prove his theory that white light is made of the spectrum of colors, he invented a new type of telescope. And this was a reflecting telescope, or Newtonian telescope. And here this is a mirror now, made of speculum. And this was, again, about the same size as Galileo's telescope, 1.3 inch. So this is tiny, that's on this little ball gimbal mount switcher. But this is the Newtonian telescope, visual eyepiece. So this is the Newtonian telescope. You look at the eyepiece, there's a reflector. It goes to one spherical mirror here, and it looks out, whereas this is the standard Galilean refractor, two eyepieces. So now by, you know, this was 1670 or so, we have two types of telescopes kind of kicking around. And it's funny, people at the time, it's weird, like technology like this, like things that you can build out of wood, people would argue whether or not this thing functions. And think about this, most people wouldn't have access to it, right? He built one of these, that was it. And then he used it, did his thing, and then donated it to the Royal Society, and it sat. Yeah.
If I'm not wrong, I think there's an anecdote that Newton built it during a period of lockdown. So they had a lockdown that time.
For the plague, yeah. For the
and
plague.
he was home for this entire period, and he just built it by himself. So motivations for our lockdown.
Yeah, he absolutely built that whole thing, by himself. And I know he did a lot of work during the plague lockdowns. Okay, so, you know, most telescopes that you see now are reflectors. And it's funny, I think you kind of think of, I tend to think of things like, oh, then we got the reflector and everything was big. At the time, and there's a few reasons for that, which I'll touch on at various points. But at the time, this was really hard to use. First of all, what you were using as reflectors was called speculum, which was expensive and heavy, made of copper and tin. You would have to cast it. It was really difficult to polish. Then it tarnished like basically immediately. So the resulting surface only was about 50% efficient. So you could make these things, but they were not like the panacea that everybody adopted. So next on our stop is Herschel, who was a German musician. And the story goes, he was a traveling musician from Germany, but working in England. And at night, he would travel from town to town and just stare up at the stars and inspire. And so he became fascinated with astronomy and started building his own telescope. So this is a bigger Newtonian telescope. This is now 6-inch diameter. And with this, he discovered Uranus, the first object not known to the ancients. Okay. So think about this. I will make a bold statement and say that for at least 100,000 years, quite possibly 1 million years, humanoids would have known about the sun, obviously, the moon, obviously, the Milky Way, and you would have really noticed these 5 planets because they're the brightest thing after the moon, and they move differently than the whole rest of the celestial sky. They're really obvious. And on average, half of every 24-hour period is dark, so they're up, and it's the only thing you can look at when you're not staring at the fire and trying not to get eaten by a lion. So the ancients, for sure, like going way back, would have known about these planets. And the first thing discovered that the ancients didn't know about was Herschel with this new technology, this telescope. He discovered Uranus. And again, these are all also, remember, on the ecliptic. The solar system's flat, so the sky, they're all in a line. Really obvious. You know, if you've ever lived in a city, like LA, you can't see stars, but you can always see the planets. It's the only thing up there. There's like the planes coming into LAX, which are like, is that Venus? Or no, plane. And then when they're up on the sky, it's the planets. They're really easy to spot in a big city. They're harder to find, if anything, you know, when you're like out in the desert and there's just so much out to see. Okay, so he discovered Uranus, and then he continued, and then after that he became famous, and the king made him the royal astronomer and gave him like a stipend. It was pretty like a good, like he had a good living. So then he started building bigger and bigger telescopes, and he went up to 47 inches, 4 foot, 1.2 diameter plus. That was great, but it was the largest in the world until 1845. But really cumbersome and unwieldy. I mean, look, this is built out of wood with like pulleys and stuff. It's not like exactly easy to observe with. This thing looks a whole lot like one of those little dogs, like just a bucket, and you go and point at the thing you want to look at. Really easy to observe with. Trivial to set up, move around. This thing required assistance, and even then you're looking through this kind of crappy mirror. What are you doing? Sketching things? You know, I'll come back to that. But it was difficult to observe. So there were not a lot of big discoveries. But I do want to, I'll use this point to talk about two main types of telescope mounts, which had not been developed yet. So one is just really easy alt-azimuth mount, which is you can move left and right, up and down, okay? That's the simplest one. The problem is, that's not how things move across the sky. Right? The sky, they're going like this. So at some point, people, and on my next slide, people just built the equatorial mount, which allows just, sets it, which allows just, you set your declination, and then your, and then you just move along the equator like that. Okay, so you pick one thing, and then you just move one motion, and it tracks the sky. And that was kind of the first modern observatories. It was here, this was the great 9-inch Dorpat refractor in Estonia at the time by Fraunhofer, who was, he wasn't a professor or anything. He worked at what became Zeiss and worked out all modern optics. And so this was the state-of-the-art scientific equipment, piece of equipment at the time. That was the first modern, like, achromat refractor. It was the largest in the world at the time. And it had this equatorial mount with a clock drive, meaning you set your declination and then just have a clock start moving with a tiny little motor, and you can track the sky, and it's just going automatically on one object at a time. So that was a big development. And so while reflectors could be much bigger, they were like crude, cumbersome, hard to use things. These were the state-of-the-art, much better instruments, the reflectors, for a long time. That didn't stop people building big things. After Herschel, Lord Ross from Ireland built what was called the Leviathan of Parsonstown in 1845. This was the largest until 1917, basically, the modern telescope. But that's just a Newtonian telescope. Here, this is, masonry now at his estate. But this was kind of like the field, this was a somewhat typical astronomer, like landed gentry, who did this as a hobby. Built his own telescope, did this as a scale. And a few kind of problems with this were that what would you do? So yeah, you could go look at objects, and then you could sketch them, okay? And you would show your friends, look what I saw, it's crazy. And he thought this was an island universe, or later they thought maybe they were like solar systems being born. But he would sketch this and then think about how you would transfer this knowledge. Who would verify it? Who else had that telescope? You're the only one. Then you would sketch it by hand and show somebody. So you'd go show it to your colleague or friend or competitor and be like, I saw this. They'd be like, no, you didn't. And that was it. That was like where the debate stopped, right there. Was that there was no way to reproduce or share, it didn't know, or share information. It was just a rich guy had a telescope, drew a sketch. You know, it was not an effective.
Computer, right?
I think it's a projector.
The computer's on. The projector's just deciding it doesn't want to be on.
It's overheating.
My computer's on and I still see it on the screen.
It's overheating.
And that's what it seems to be. So what was, well, I'll go forward. The thing that really solved this was another technological revolution, which was chemistry. And chemistry enabled what? Photography. Photographic plates. So that enabled three crucial innovations in astronomy. One was that once you got over technical difficulties, it wasn't instant. It took 50 years of development. But once you were able to, then you could integrate longer. You could track with your telescope and keep collecting photons. And so you could observe deeper than not only with a bigger aperture, but also more sensitively than just your naked eye was detecting photons. Okay. Also, it enabled you to do spectroscopy. So to disperse light and record that dispersion of light, okay, that was the advent of astrophysics. Astronomy was just taking pretty pictures and wondering what they are. Astrophysics was linking, and that was what Fraunhofer did, was realizing that the stuff here is the same as the stuff out there, and we can look at its atomic fingerprint by dispersing its light and cooling that. Okay? And the third thing that really revolutionized things, any guesses? I kind of touched on it already. The ability to transmit information and record it and then debate it, right? Before that, it was literally just I looked with my homemade telescope and somebody else would be like, no, your telescope's broken. Literally, these were the debates. There were debates about these telescopes saying oh, it's stuff on the mirror. It's not real because I didn't see it. And it turns out the other guy's telescope was broken. So there were all these stupid debates in astronomy. I saw this thing, no you didn't. And so finally, and even the first photographic images, people debated that, but eventually that all got settled, and then this was really a scientific record, right? Was photography. Okay, so I'm going to skip a little bit of history. Oh, okay. I'll go over. The next kind of big development was so they developed how to make nice glass. They developed how to make nice mounts. They weren't totally finished there. Then they figured out to go up on a mountaintop. Okay? And people had done that myself, but the really first major observatory was Lick Observatory, which was on Mount Hamilton above San Jose. So above Silicon Valley, you could look, you see it up on the hill. Really nice drive up. And you can just drive up and go see this thing. It was a 36-inch James Lick detector. So James Lick was it railroads? He was one of these robber baron guys. And he knew he was going to die, and so he was casting around for something to commemorate his greatness. And at first he wanted to build, I shit you not, a pyramid in San Francisco. And then, I forget which astronomer it was exactly, came and convinced him, you could build a scientific observatory on the top of the mountain that everybody could see that would expand our view of the universe. And build the biggest telescope ever. So this is what he was convinced of the biggest. And so they built a 3-foot refractor. And here you started to really run into the limitations of these refractors. My next slide, let's see. There was the Lick Observatory. Again, another rich person here, he's from Chicago. They built it for the University of Chicago outside of Wisconsin, not on a mountaintop, mistake. And they tried to build a bigger one, and this was the end of the line. This was the biggest refractor ever built. This observatory was considered kind of the birthplace of modern astrophysics. That's where Hubble got his PhD. It was the first modern standalone observatory, laboratory, academic department. It's funny, like I did my PhD at the University of Chicago, but I was in physics. But by that time, even the astronomy department was no longer located in Yorkie's, it was on campus. And like a few years ago, I met a really old dude. So old, he's from Germany. His name was still Adolf. Like he was born, before you could no longer name your kid Adolf, right? Super sweet guy, awesome. And he was a grad student at Yerkes, or at Chicago, which was meant at Yerkes. And he was telling me how, I feel sorry for you kids, because you guys did your PhD on campus. And you think about all this like talk these days about work-life balance and everything. Back then you were a grad student at work and you lived there and ate there and all of your meals were there underneath your professor, like side by side with your professor. And we think about that as kind of like horrific now, but back then it was like, oh, it's amazing, because you go and there's the professors, there's the technicians, there's the engineers and the students, and you're just all right there, all 10 of you just there taking your meals 24 hours a day. And he was like, that was amazing. Different times. Okay, so this was in the line. If you go look at our 12-inch telescope though, it's the same mount manufacturer, same company makes the glass. So it's just a mini one of those. So go check that out. And again, every first Friday, it's open to the public. Or if you email me, we can arrange to go see. There were a few problems with these refracting telescopes. Chromatic aberration. So this basically different wavelengths of light, have different because of the index of refraction of glass, have different foci points. And so you get, chromatic aberration, meaning the red and the blue are totally different things. And then you get reflection and losses at each surface, right? Typically about like 1/3 of the light bounces off each surface. So you can do some tricks to fix this, but these are basically fundamental limitations. Then transmission loss, especially towards the blue, where the bigger aperture you make, the thicker it's getting in the middle, okay? And the more perfect that glass has to be. You can't have any bubbles in this. So the bigger you make it, you're making this thing that's like nearly a ton, and it has to be perfect. So it was just a real pain. Then these things are getting really heavy, and they're hanging off the end of a tube. So you're getting flexure. So you can't point the thing accurately. So you're hitting all these engineering challenges. And then to mitigate the chromatic aberration, you have to make a really high F number, which means really long tube, which means more sag, and which means this giant dome. Okay, so all these things are just, it's end of the line of what they can do, okay? So the next thing that was coming was again kind of advances in chemistry, which was silver glass. So to make these mirrors, you take a piece of glass, not metal, you take glass and you polish it. But now you don't care if there's bubbles in it, because you only care about the surface. So you can cast it and you just care about that surface. You can have bubbles all the way through it, doesn't matter. And then you just deposit silver on the top surface of it. And there you have it. So this was a big innovation. And you could easily figure glass the right shape, polish it to a high degree of accuracy, and then just silver glass on it. And the first such telescopes were built by amateur astronomers. He was a doctor, not a fake doctor like me, like an actual medical doctor. Andrew Common in the 1870s and 80s, and he eventually built up to a 36-inch refractor. He was in the south of London, and was just an amateur building these things. And this culminated basically in the Hale 60-inch, which I'll get to in a second, but that's all modern, for the most part, all modern telescopes are made like this. Okay, we can skip Messier. Okay, let's get back a little bit. We're gonna come back to photographic clips. Okay, so now you've got good mounts, good mirrors, photography, okay, and now we're about 1900. And this was another amateur, Isaac Roberts. He was a pioneer of using photographic plates, and he started the field of astrophotography. And this was considered his magnum opus. This was a 1 hour exposure with a 20-inch reflector. So yay big, and he got it to track well enough to take a 1 hour exposure and expose this. And just to show you where this is, so here's the Milky Way. Oops. Just zoom in. That guy right there, that fuzzy blob, was kind of an awkward type of object on the sky for astronomers to explain, because people had known about these for a while. Messier had cataloged a whole bunch of them. They didn't know what they were, okay? And Roberts thought this was maybe a solar system in the process of forming. But as technology improved, and this is what it looks like today, I'll come back to it. As technology improved and professional astronomers started getting into using these telescopes, like it started with that amateur, Andrew Common, donated his 36-inch reflector to Lick Observatory. So remember, this amateur made this 36-inch reflector, and it goes to the same observatory at Lick as this 36-inch refractor, okay? And they started using it with photography. And they're cumbersome to use. People, it wasn't a conventional telescope, astronomers were used to refractors, so they complained about it. But then they started using it with photography, and it really revolutionized everything. So professional astronomers now, these were people that were trained, and this was their job, started systematically taking pictures of these nebulae with early photography plates and early reflectors. And then they started debating about what these were. And one key piece of information was happening at Harvard, where basically there was one director that was a man, and then he would have a whole slew of computers or assistants that were not allowed at the telescopes, but they would look at the data, and they were all women, basically because he could hire them cheaply. And they were really highly motivated and really smart, often with college degrees. And they made all the seminal discoveries of the last century, including this one by Henrietta Leavitt, that she discovered that some stars pulsate with a period that's proportional to their luminosity. So if you measure the period, you can tell its absolute luminosity. So this is now a standard candle. So if you measure the period, you can tell how bright you observe it to be, and thus how bright it is intrinsically, thus a distance. Distance is really hard to describe. Angles are pretty easy, distances are hard. So this was a huge thing. And then we had kind of everything in place for this great debate in 1940. And it was basically this technology limit of fuzzy blobs, then you have photographic plate. Here's where we are in the modern era, but in this kind of era, people were debating about what these were. And this was profound. So some people, namely Harlow Shapley, who at the time was at Mount Wilson, but he was in Pasadena, but he was about to become, after this debate, he was famous enough, he became the director of Harvard Observatory. So so debates between, you want it? Okay. And they had great names. Heber Curtis and Harlow Shapley. And they were kind of the two most eminent astronomers in the US. And Heber Curtis said that these fuzzy things out there must be outside of the Milky Way and island universes. At the time, the Milky Way was the whole universe. Talking about something outside the Milky Way was stupid. A whole other universe, a whole other universe. And they knew there were these fuzzy blobs all over the place. So that means that okay, all these fuzzy blobs are other universes. It was kind of crazy. And these universes would be so far away, it would take light millions of years to travel to us. They're millions of light years away. This was crazy, clearly a crazy proposition. And then Harlow Shapley was saying, oh, they must be clouds in our galaxy moving really fast, which was also kind of crazy. What made them move so fast?
I guess by this time, the speed of light was pretty well measured.
They knew it was finite.
Okay.
It had been measured. And so the first inaugural National Academy of Sciences was held. And a person that's going to come up again and again is this is Hale. and his dad was rich, and he got his dad to fund the National Academy of Sciences, and then it meant like he got to pick what the first topic was. And they picked this as the inaugural debate for the National Academy of Sciences. And so they had this actual formal debate, weighing pros and cons. And then it was left at that. And everybody actually thought Harlow Shapley's arguments were better, even though he later turned out to be wrong. He was just a more dynamic speaker. And so we're almost there. The next big technology was the Hooker 100-inch reflecting telescope. My guy Hale, who was this rich kid, it was actually interesting. He got his undergrad, his dad invented, I think, grain elevators, or had the company that did grain elevators, so was rich in Chicago. He went to MIT as an undergrad. Then for his graduation gift, his daddy bought him a 15-inch refractor in Hyde Park. So he had his own observatory after graduating college. That was his graduation gift, a 15-inch, which at the time was like the biggest in the US. Like, not counting the two, like, not like Joachim's, but basically comparable. We only got ours in like 1910 or something, and that was a 12-inch. So the University of Illinois, the state flagship telescope, was like 20 years after his and was smaller than the one he had. Then University of Chicago had just been founded and wanted that telescope because it was in their backyard. So they go to the dad, they're like, hey, we want that telescope. Can you donate it to us? And then we have an observatory. And the dad was like, how about if you hire my son as a faculty member? Then you can have his toy telescope and I'll endow his position, meaning I'll pay his salary. And so that's how he became a professional astronomer. Then he had this network of like rich people, because he's rich, and he started building the biggest telescopes. Starting with, he built Yerkes, which were refractory, and like halfway through that he realized the engineering limitations, so then started moving to reflectors. And to mountaintop observatories, he found one up above LA. You can drive up there, it's really cool to go to. And this is the Hooker 100-inch reflecting telescope. And I don't have the 16-inch. Why didn't I put the 16-inch? Oh, stupid. There's the 16-inch that he built before this, where he kind of worked everything out, and then he built the 100-inch. And when, this is now like, it's not really used for research. And when I was an undergrad at UCLA, somehow the ownership of this observatory had gone to UCLA where I was an undergrad. And it was like how here at Illinois, the undergrads have our little 12-inch telescope. At UCLA, we had this. But for some reason they were still using this for stuff, so we couldn't use the 100-inch, we had to use the 60-inch. And we'd go up there with like cases of beer and camp and like just mess around. And I didn't, back then when I was 20, I really didn't appreciate all the history of it. But, so this was the second version of the 100-inch, not the 60-inch. It was built in 1917, it was the largest until 1949. And this was, as soon as Hubble finished his PhD, this is where he was hired to observe on this. And this is where he really used this to discover the universe. And one other thing. Remember we talked about different technologies coming along. What was the technology that enabled this? Well, this. What's it look like? If you just look at that structure. Steel. Right? This was think of when were the first skyscrapers being built in Chicago? 1880, 1890? When were the first steel bridges being built? 1890, like Eads Bridge over the Mississippi and St. Louis. So steel was this new material that people were using. And again, it was controversial. People were like, oh, it'll break. You don't know. It's like how we talk about carbon fiber on bikes now. We're like, oh, it's great until it breaks, And people will say the same thing about steel. But here they quickly incorporated it into these telescopes. And this is something, the size of a bridge that moves with the precision of a clock. This was a huge technical masterpiece, right? This was no longer like amateur gentlemen astronomers. This was like a major feat of engineering. Okay, so Hubble was hired right after his PhD, and he thought a cool problem would be to go start measuring distances to these things using the Cepheid technique. And in 1923, he finally measured the distance to Andromeda, And it turned out to be 1 million light years away. And this completely revolutionized our understanding of the universe. Because now, every galaxy that we see, every fuzzy blob that we see out there is a whole nother island universe now we know is a galaxy. But that really revolutionized it. Okay, and then he kept doing that, and then, kind of without credit, started taking somebody in Arizona was measuring the velocities of these things with just Doppler shift, and then he, without citing it, put these together, and then noticed that, but this was his insight, was noticing this relationship, was noticing that the farther away objects were, the faster they were moving away from us. So if the universe were just static, say a galaxy were moving around, you'd expect that some could be moving farther, close, nearer or farther, but it'd be, the average would be 0, right? Some are moving towards us, some are moving further. Instead, what he saw was that, on average, the further away they're moving faster away from us, okay? And this was huge. We didn't know, and this is 1929. We didn't know how stars burned until like 1935. So before we understood how stars worked, we knew the universe was expanding. And then people started thinking about what this meant. So if you just play that backwards, so right now you measure, and again, this is not very sophisticated. Well, okay, granted it's a nice telescope, but crude instruments, like photographic plates. So now an enterprising young undergrad could get a telescope and a CCD and do this measurement today, right? Of course we use way more sophisticated things, but you could. So if you play this backwards, so measure this now, the universe is expanding. So you play this backwards, the universe had to be denser in the past. And if it's denser, it means it's hotter. And if you play that all the way back, at some point it was just this dense plasma, okay? Now play that forward from the dense plasma. It means that you started with some point and it expanded, eventually cooled enough such that protons could find the electrons, form atoms, then the universe is neutral, and now photons can stream, okay? And so we can look back and see that moment in time. Because remember, a telescope is a time machine. So you just have to look back to that temperature or time, and you can see this. And indeed, we do. And that's called the cosmic microwave background. And it was accidentally discovered in 1965 by 2 researchers at Bell Labs, Arnold Penzias and Robert Wilson, Wilson just passed away. And this was the middle.
Arnold just passed away.
Wait, that was Bob. Penzias passed away.
Arnold Penzias passed away like 2 weeks ago, 2
Yeah.
weeks ago.
Yeah, okay, I got them mixed up,
Yeah.
right. Penzias.
Yeah.
And again, why were they doing this? What was going on in 1965? Globally. It was a big race. Space really big race, space race. Okay? The 2 world superpowers were racing to be dominant in space, right? And Bell Labs was the telephone company. Nowadays we think about that as like the telephone company, like it's always a joke. But back then, there was a rule. The telephone company, just to allow people to like communicate across the continent, there was a rule that they were allowed a monopoly, but they had to take 10% of their profits and put it into basic research. Bell Labs has more Nobel Prizes than the University of Illinois.
Wow. Way more.
Way more.
Way more.
Way more.
More than any other institution in the United States.
Yeah.
It was a crown jewel.
Yeah. They invented the transistor, CCDs, discovered the Big Bang. It goes on and on and on and on, okay? And these guys were trying to, they're a phone company. There's a space race going on. What are space communications gonna look like? Let's go measure the background. That was their problem. Let's go see what noise is out there. So they built this big dish, 1 pixel, and started just trying to measure the noise. And everywhere they looked, they saw this hiss. Everywhere. And they assumed it was like a problem with the instrument. Check the instrument, not the instrument. And they rule out everything. They even climb in here and scrape out all the pigeon shit. Like everything. They tried everything. And then finally, they measured an excess of noise, and that was the Big Bang, and they won the Nobel Prize. Then we started launching satellites to measure this. And those measurements have gotten better over time. This was 1992, Nobel Prize. WMAP 2003, Plonk 2013, getting better and better. And just to give you a sense of this is all sky image. So picture just what we're looking at. Okay, picture of the Earth, right? It's a globe. It's not fun. Okay, but then when we look at a map, you take that three-dimensional surface and spread it out in 2 dimensions, right? So here we've taken the sky, and this is the radiation all around us, and then just put it in 2 dimensions. So that's what you're looking at. So this is like if you looked all around you. You see
Even
this.
underneath you.
Yeah. Because we go up in space and spin this thing around.
So middle is above you and the sides are underneath you? Okay.
That's in galactic coordinates, so not quite, but yeah. It's in that this one is put relative to our location in the galaxy, such that I can show you on another thing, but basically our plane of the galaxy starts this way in that projection, in that orientation. But that thing that you can't see right now is an honest to God photograph of the beginning. We put a little camera on a little mirror up in space, spun that thing around, took a picture. It's a picture. Looking all the way back to the beginning. And come up. I think the fan must be off or something. Somebody blows on it.
Can I ask you a question while we're waiting?
Yeah, yeah, go ahead.
How did the landed gentry, in the early days of astronomy, how did they make sure they're talking about the same thing? Like, oh, I was looking at that direction. And you're like, nah, I was looking
Oh,
over
on the
there."
sky?
Yeah, how do they make sure they're talking about the same thing?
So they did have a coordinate system. They had a coordinate system.
Huh.
And then, but also like one of the ways normally you orient yourself were the constellations. So you would know what group of stars you're looking at, and then offsets from them.
I see.
I think the more profound question is how do they do those measurements, right? But it's all offsets. So relative angle measurements are easy. Absolute ones are quite hard.
Yeah.
And most modern telescopes do not have good absolute pointing. Even like the ones I'm going to get to, like even Jacob's T. Where you are exactly, you can get it to about a degree, but then the fine adjustment is you look at the other stars around you, compare that to a map, and then fine adjust.
Oh, right on.
Yeah, that navigate, like the most detailed navigation is always from the stars. Always has been, still is. Just to give you a sense of scale, this is that Planck satellite that operated from 2009 to 2013. This is now. We know what this is. These kids have probably never seen it. Has anybody who's ridden in one of these? Well done.
I drove one.
Huh?
I drove one.
But what
Oh yeah, my grandpa has one.
Yeah, so it's about the size of a VW bug. It's a mirror with some cameras. It's all held cryogenic temperature. So this is held at 100 millikelvin, so 0.1 degrees above absolute zero. The detectors have to be sensitive when it spins you out. That's how that image was made. But again, this is an actual honest to God baby picture of the universe. And if you take, so the universe is 14 billion years old. If you make that into a human lifetime, 70 years, this is the equivalent of taking a picture of the universe when it was 1 day old in human lifetime. Okay. But it's just a photograph. Okay, next big thing back to Hale, guy with the rich dad and rich friends. He starts building the 200 inch, okay? He builds the 60 inch, the 100 inch, the 200 inch. Planning began in 1928. They started the mirror in 1934. Nobody knew how to build any of this at the time. Like everything was state of the art. How to make the bearings, how to pour the glass. Everything was state of the art. Then war happened. That's what was going on there. Then Hale died. And then finally, the first sight was 1949. And the first observer, as kind of honorary, was Edwin Hubble. And then it had this illustrious career as just state-of-the-art telescope. This is an actual photograph of it. Oh, this is the 3D model of it, and these are all to the same scale. This is the 200-inch Hale, so 5 meters. This is what I physically built. This is the 10-meter South Pole telescope that takes the most high-resolution pictures of the cosmic microwave background. This is a 2.5-meter Hubble telescope, which you can see a copy of, or like a life-size rendition of it in the Smithsonian in DC. It's big, it's impressive. And then this is JWST, 6.5 meters.
What's the last one?
James Webb Space Telescope. I'll get to that.
James, yeah, James Webb.
Webb. Okay, and then there, just the dome for scale. That's neat. Has this beautiful Art Deco. They spared no expense back in the day. The Russians tried to compete with it in 1976. They kind of like overshot. It's interesting. So they built a bigger one. They managed to do that. And it was really the first modern telescope, but it was a failure. But they used all the modern things that eventually were adopted kind of in the 80s by the West, 80s and 90s. But here's a plot, because I put everything together. So here's diameter, so square that for collecting area, versus year. And kind of you see where all the technologies kind of crap out. So these are refractors, then metal reflectors, so like where the reflector is speculum, and then glass reflectors. And you see what it is, and then getting telescopes, optical telescopes at least, up into space. And so you kind of see this is how technology marches on and then peters out basically. It hits technology limitations. That's where we're at right now. And basically we've maxed out every one of these. We'll talk about it. And here, yeah, I'll show this. This is the other kind of dimension, which is year again, but now your sensitivity to flux. And so here you see around 1900 it going up because of photography. Basically, it's you could just sit and stare and collect more photons from faint objects. And then the CCD kicking in the 80s. Nowadays, the space telescopes are way up there. But it just kind of shows you these technology developments. Okay, then we get the space race. Saturn V, we needed Saturn V to get these things up. We had to go to the moon. Then we developed the shuttle. Then we had things like NASA's Great Observatories and Hubble Space Telescope, which was launched in 1990. At first, it was a failure. It was a laughingstock. They set the surface of the mirror wrong. What's crazy is that for years, for 30 years, this Hubble telescope was the fanciest, most expensive, complicated telescope humans have ever built. Ever. And it's still state of the art. I mean, okay, it's not state of the art, but it's still like cutting edge. This is a mere Ford compared to the Cadillacs the military has printed down. This was a copy of the ones they were making. You know, the shuttle was made to launch military satellites. It's big, this size, to put military satellites up. Oh yeah, we'll do science too. You know, those were the things they talked about in public. But so for that's been up there for 30 years. They launched like, I don't know, the Keystone project I think was like between 30 and 60 telescopes looking down that were all Hubbles looking down. You want to take have as high a detail as you can. So whereas for space telescopes we want it as far away from Earth as we can to get away from the glow and the radiation from Earth. If you're looking down, you want it as close to Earth as you can. And it turns out the atmosphere and the drag from the atmosphere is really stochastic and uncertain. And so every year they would lose one of these. So whereas like we have this thing up for 30 years, the military is just burning one up in the atmosphere like literally every year. Nowadays they've gone away from that and they're doing smaller stuff. And the last one they had like sitting in the lab, they gave to us like 20 years later, and that's the telescope after JWST is that mirror that they had just sitting around. Weren't gonna do anything. I'll come back to that. But look up the Keystone project if you want to see that. So that the space race and the show, that kind of culminated in us getting off the ground and into space. And then we did that at other wavelengths as well. So the gamma rays, X-rays, infrared. And these were all kind of, depending on how you count, billion-dollar class, in some cases up to 10 billion. Again, it depends on how you convert and if you count the lifetime operational costs and all that. But these are, you know, a major facility or a great observatory is typically about $10 million. And that was what JWST was just to launch. And operating it would be a lot more. This image taken with Hubble is one of the most spectacular, like I would say the two most spectacular greatest hits images, the cosmic microwave background from Planck that I showed you, and then this deep Hubble image, which JWST is now doing even better. But basically, this was, imagine we take a pea, put it between your fingers, and you hold it at arm's length. And you project that onto the sky, okay? It's a tiny little patch of sky. That's the size of this image. And they intentionally, and this was a new thing, they intentionally pointed, the director pointed, once they fixed everything, they fixed the mirror. Oh, I forgot that tangent. Yeah, the military messed up, and they mismade the mirror for this one. So they had to put in a correcting lens. Then it worked great. Okay, so then the director, once it was working, decided to take a deep field and a blank patch of sky. Deliberately point at the blankest patch of sky we knew at the time. There was like a whole team of postdocs that were calculating what was the blankest patch of sky they could find. Mark Dickinson, you probably heard his name. He was one of them. And so then they sat and they stared for like a month straight, just staring at this patch. And this is that image. Everything in here, okay, there's like 5 stars in here. Can you spot them? Stars create diffraction spikes because it's a delta function basically, and then it interacts with the pixels in the CCD, and so you get these spikes when it's a delta function. When it's resolved, you don't. So the only stars in there's like 1, 2, 3. I might have covered one. There's maybe 2 others in there. Every other thing in here is a galaxy. This, again, a pea held at arm's length. This is like a tiny fraction of the sky.
Even the small dots.
Everything. Okay, but you know what else is crazier? Take the average color in that map. What's the average color?
Orange.
This is not a trick question.
Would be red.
It's not a trick question.
Black.
Black. Now think about this. If the universe were infinite and not evolved, what color would this be? Yeah. Because wherever you look, you can see a galaxy. Wherever you look, right? So we can just take a picture and look and see that the universe has evolved. Right? Along this line of sight, we're not looking at any galaxy. Okay? And then beyond that, but beyond that is that cosmic microwave background from the beginning. Right?
Is it a visible wavelength?
Yeah, really close to it. A little bit more to the infrared. And those, do you know who owns those images? Huh?
NASA.
You do!
NASA, yeah.
Anything NASA takes is public. So you, the taxpayers, own it. It's public. You can go download that thing. It's like 300 megabytes for the, close to full resolution, but you can zoom in on any patch of sky. It's a galaxy all over. And JRC is now taking these. It will take better and better over time. Yeah. It's really, really always fun to just zoom around. And if the projector were working, I'd zoom around with you right now. Where are we on time? Okay, I'm gonna quickly, I'll talk about one more thing of just future, how we got around the next hurdle in mirrors, and then finish up. Assuming you get there. Okay, so the next thing that we maxed out on with mirrors was these were monolithic 5-meter chunks of glass. And they sagged under their own weight. And they were really expensive to build. You had to invent a new type of glass, Pyrex, glass that had really low extension. Okay, but that was a limit. Like the bigger you make it, the heavier it is, the more gravitational sag there is. And so people were trying to get around this. And basically 2 technologies were developed. One at Arizona, at the National Optical Facility in the University of Arizona, and the other in California, at the University of California by a physicist. And these 2 methods were, one was spin casting. So he started by taking literally broken Pyrex glasses, putting them in a kiln, in an oven, and then rotating the thing and letting it melt. And by rotating it, it'll make that shape and it'll cast it and be thin. Okay? So spin casting. And then the other technology was making a bunch of smaller mirrors that you put together. Okay, so these were classical mirrors. That was how Hubble made them. They still lightweight. Then honeycomb mirrors, where you put stuff in there. Meniscus mirrors, which was you basically spin, or all of these are kind of spun cast, and then segmented mirrors. And the guy that did this, Jerry Nelson, passed away like a year or two ago. And it was interesting because it was a physicist from LBL and he came up with it. So eventually they got around, you know, this 1940s technology, but you had to kind of wait for new technology in mirror development, and really it was computers. You had to wait for computers. Because all of these things have to be set and controlled with actuators, and so you needed sophisticated computers. And there's me in the mirror, a little selfie in that mirror, but this is the 10-meter Keck telescope. And then by the 90s, people started building more 10-meter telescopes. And the next big thing is, the next big leap after 10 meters is going to be a 30-meter class telescope, which the US is losing this race. We have two designs. There's basically two same technologies. There's like two camps, and they don't agree, and then like in a blood feud. Making multiple big monolithic mirrors or many small segmented ones. And then, that's the European one, this one. Then meanwhile, the Europeans have just adopted this technology and are running with it, and are gonna be on the sky sooner than us with a better telescope, bigger one, and better instruments. And it'll be the first time since like Herschel that Europe has had a better telescope in the optical of the US. But you know, we still dominated in space and in all the other wavelengths. So. Okay. I met the hour, so I'm gonna stop. I'll show you one more thing, just that development. So this is M51, another spiral nebula. The Whirlpool Galaxy. This is the sketch by Lord Ross. That's photographic plates. This was done by the first kind of modern photographic survey of the sky from the 1950s. It was funded by the National Geographic Studies, done by Caltech. This is the 40H telescope. So that's a photographic plate. CCDs, this was done from the ground with a 2.5-meter telescope. That was the first modern CCD survey. And then that's Hubble, same aperture but up in space, so you really see the effect of the sky and scene. And then Hubble, and then a different one, but you see now we have the Webb Space Telescope. And there's the primary mirror from Hubble compared to James Webb. There's the diagram of Webb. I happen to be one of the first people to use it. There's strong lens galaxies, whole other thing. There was the technological limit now. The space telescopes is a launch vehicle. So the biggest launch vehicle we've ever had, the most powerful. This is the Saturn V. And we don't have any more of those. That was the most powerful launch vehicle ever. This was built with drawings by hand. It was before really computers. And the people that built them by hand, like Ferraris, were dead. And so all the other things have been smaller. But there's a few being designed that could maybe launch big things. The real limiting thing is the fairing size, the fairing diameter. So typically it's limited to 5-meter diameter fairing. And that's practical limit is what you can put on a shipping container on a giant ship. But then it's like there's never been a need for anything bigger. But what that means is that if you try to launch a 6-meter telescope, you've got to fold it out by origami. Okay? And the process of making things that do that requires a lot of engineering. And you know, the actual material, yeah, that's gold plated, but you're talking about like hundreds of thousands of dollars. On any instrument like this, the cost is people. So it was $10 billion because it took a lot of engineers to design this thing over the years. The actual cost is, you know, maybe 500 million now. And so the limiting thing is really this fairing size. And if you could make a bigger fairing, you could just plop JBST in there and just shot it up into space, and not have all these moving parts, and save all that cost of engineering. And so the next big, I think, enabling technology is going to be fairing sizes on rockets that are, you know, 7 meters or 10 meters. So that's nice. Okay, I'm gonna end there. Thanks. Two announcements. Who's ever seen a total eclipse? It'll change your life. It's amazing. It's the most spectacular. I was kind of like down on it, like, I don't know, as like a professional astronomer, I'm like, oh, cool, random alignments of space rocks. This one is worth seeing. And you can just drive to it and it'll be like the only thing in your lifetime. Just ditch school, it's on a Monday, drive down, it'll be worth it. The other thing is that we have, for a few years now, but it's kind of ramping up. We have this thing called Astrofest. It's April 28th was the last one. The next one is April 26th. We're about to finish the poster and then it'll be officially announced. There's a webpage though. And it's for anybody on campus interested in astro broadly defined. So yes, that includes aero, that includes people that are interested in optics, and it's kind of aimed, the goal of it is just to bring together all like-minded researchers and see what else is going on campus. It's free, registration's free, but we want you to register mainly to get a head count for food, there's lunch and everything. And there's talks, poster session, so it's a good excuse for an undergrad to make a poster. If you're a grad student, just drag an old poster you have, and you'll meet kind of all the other like-minded folks. It's like a party. Nice.
And we can send an email reminder about the Astrofest.
Yeah.
Yeah. So we had a couple questions during the talk. Does anyone have any other final questions?
I guess for the cosmic microwave background, like when you look up at space, like different parts are farther and older in time than other parts. So is that like the same idea for the cosmic microwave background, or is it all the same age?
The first order, it's all the same age because there's this moment in time when the universe cooled. And so we're actually seeing a thing that's like a surface that we're seeing that moment in time when the universe cooled enough such that hydrogen could form and the universe became neutral. Second order, some of the spots were hotter and colder from quantum mechanical fluctuations that expanded. So at a small level, that's not precisely true, but both you're seeing one surface.
Cool. Great. Nothing else. Let's thank the speaker again. Pizza outside room.